lecture, we will solve some questions related to wireless digital communication. We will start with the first question. The first question says, diversity in wireless communication means what? Is it sending the same signal over independent paths to improve reliability? Or is it receiving the same signal from independent paths to enhance reliability? Or is it sending or receiving the same signal over or from correlated dependent paths? And D, is it sending or receiving the same signal over or from independent paths to improve reliability performance by reducing fading effect? So remember with me, diversity is transmitting or receiving the same signal from two independent paths, two independent ways, seeing different channels. So the correct answer is D. It's not just transmitting, it's not just receiving, and it's not the most important thing about diversity. The paths the signal take, they are not correlated, they are independent. Okay? The second question. Diversity in wireless communication can exist in time domain only, frequency domain only, space domain only, or time, frequency, space, polarization, angle, and site. Which one is correct? So the correct answer is D. Why D? Because remember with me, diversity can exist in time, in space like this. Diversity can exist in time where you send the same symbol in two time slots. You send it in the first round and you send the same symbol in the second round, but making sure that the second time slot experience a different channel. If this experiences H1, this should experience a completely independent channel, H2. And it can happen in the same frequency, let's say this time 1, time 2, it can happen also in F1, F2. In the frequency of F1, you send the signal X, and in the frequency of F2, you send the same signal again, X. And these are independent, of course, because they are on different frequencies. So the same thing can happen also in polarization. Polarization, we know antenna can be polarized vertically or horizontally. So if you send the same signal, X from here and X from here, this means that you are sending the same signal in an independent way, and this is also a type of diversity. And angle, you can send the same signal from this angle and the same signal from a different angle, and due to reflection, they can reach the receiver. This hits maybe a building or mountain, and this hits a tree or car, and gets reflected here, gets reflected here, but you are changing the angle, and you can also use diversity with style. Like you have here a tower or cell, and you have here another tower, and you have users here, and the signal here is the same signal here for X1 and X2. You are sending them from two base stations. So basically, you get the signal from tower 1 and tower 2, or cell 1 and cell 2, base station 1 and base station 2. So the correct answer is D. And there are also some other types of diversities that we didn't talk about in this course, but like in the future, you may encounter them if you specialize in wireless communication. Question 3. Give me an example on a diversity technique that exploits time domain in wireless communication, wireless transmission. Give me a diversity technique that exploits time, not frequency, not space, not site, not polarization, not anything, just time. Which one is true? Is it frequency hopping spread spectrum? You have to know what frequency hopping spread spectrum is. You have to know, is it data multi-coding or space-time block coding? Or is it coordinated multiple points? Each and every term here, you should know how to define it, and you should draw a picture in your mind when you see this term. Or is it automatic repeat request? In time, I'm saying time. A diversity technique that exploits time domain. So the correct answer is D. D, automatic repeat request is exploiting time. Why automatic repeat request is exploiting time? Let's assume we have this transmitter and we have this receiver. And this transmitter sends a packet to the receiver, and this packet, unfortunately, due to bad conditions in the medium between the transmitter and receiver, the packet got dropped. So the receiver didn't decode it successfully. The receiver job is to inform the transmitter that I didn't receive it successfully. Could you please retransmit it again? The receiver will immediately retransmit the same signal again, one more time at a different time slot. And this signal, most probably because of the time delay, is going to experience and encounter a different fading channel that might probably be better than the first one, and therefore it's going to be decodable at the receiver. And in this case, you will be able to recover it or jointly sum the data in the first round with the data from the second round and decode it using maximum ratio combining. So the correct answer is automatic repeat request. The fourth question. Combining techniques at the receiver are very essential in order to benefit from diversity. Which of the following techniques can provide the best reliability performance? We have, in the case where you have a receiver here, and this receiver, this guy has two antennas, let's say. And the receiver can utilize these antennas to receive the signal transmitted to his side. And one way to use this is to use selection combining. What selection combining is basically you select the antenna with the highest gain and you take the signal from there. Let's say this antenna has gain. When I say gain, it means the channel response, H1 for this case is 0.5. And H2 here is 0.9 or 8. So which one is better to receive my signal from? This one or this? Of course this, because my signal will be multiplied by 0.9 instead of being multiplied by 0.5. So this is selection combining. Equal gain combining, I just receive this signal and this signal with a certain weight. Equal weights from all the antennas. You take all the signals from all the antennas and sum them equally without making any bias. Cognitive combining and maximum ratio combining. So the optimal way of receiving your signal if you are a receiver with multiple antennas is to use maximum ratio combining, because in this case you will receive the first signal x and multiplied by h1 conjugate, r, multiplied by h1 conjugate plus r, the same received signal. You multiply it, this is, let's say, R1 and this is R2 by H2 conjugate. And this end up, at the end of the day, you will get something like this. X multiplied by H1 square amplitude square plus H2 amplitude square. And this usually gives you the optimal performance in the case of receiving a signal from two antennas or more. So the correct answer is then D, maximum ratio combining. Now let's go to question 5, and the question says, providing diversity comes at the cost of reducing spectral efficiency or wasting some resources in time, frequency, or space that we could have used to send information, thus it reduces transmission rate, or C, increasing complexity and processing time, or all the above. Basically, this question summarized the drawbacks of diversity. Yes, diversity is a great, it improves my bit error rate. Instead of getting a bit error rate something like this, I'm getting bit error rate something like this, which is much better. I can decode my signal at a lower signal to noise ratio. But what's the price that I pay to get this gain? I reduce the spectral efficiency. Why I reduce the spectral efficiency? Because if I have two antennas and I'm sending the same signal from two antennas, I could use these two antennas to send two independent symbols, x1 and x2. But since you are utilizing them for providing diversity, you are not able to utilize them to increase your data rate. And this is one disadvantage. The second disadvantage is wasting some resources in time, frequency, or space that we could have. Basically, this is related to the first one, but it's strictly speaking about the resources. When we say resources in wireless communication, we mean time, frequency, space. This is what we exactly mean. And C, increasing complexity. Why do we have this issue? complexity issue. We have the complexity issue because you need, here when you receive the signal and do this processing, this takes time. And it takes time and power, computational power. So it adds complexity plus processing time, delay. Therefore, the correct answer is all the above, all of the above. All of them are really drawbacks of diversity. Now moving from the subject of diversity to the subject of adaptive modulation. Adaptive modulation in wireless communication. What do we mean by saying adaptive modulation? A method used for changing the transmission parameters according to the large and the small scale fading channel conditions to improve performance. Or B, a method used for modifying the transmission parameters according to the application requirements to improve performance. Or C, a method that can provide optimal data rates for different channel qualities or application requirements. D, all the above. So adaptive modulation is a technique or method where we change the modulation order. We change the modulation order from binary PPSK to QPSK to 16 QAM and so on and so forth. According to what? According to the requirements and conditions between the transmitter and receiver. So the correct answer is D. It includes the environment, according to the environment, like small scale fading, large scale fading. Give me example of small scale fading, path loss. If the user is closer to the base station, this means that the signal to noise ratio is large. And this means that I can provide higher data rate. Isn't that right? Which means I can provide 64 QAM, 128 QAM. But if the user is really far from me, I cannot provide higher order modulation. Why? Because the user will not be able to decode my signal correctly because of the path loss degradation. So to avoid this, I send PPSK to that user. And according to the application, if my application is messaging, texting, do I need high data rate? No, I need reliability more than I do need high data rate. That's why I send my data with PPSK, because I want reliable communication. So basically it's C and D, they are both correct. Like, because C it kind of talks about the application side and the channel side, but not in more details. But like D is just gathering all the answers we just mentioned. So question 2, suppose you want to serve a user device with very high data rates. Then what modulation scheme would you use among the following? That's pretty very easy. Which one? Because there are questions that are extremely very easy, and there are questions that are easy, there are questions that are difficult, and there are questions that are very difficult if you didn't read or study. So I think if you want to serve a device with high data rate, this means that you need to provide that device with the highest modulation order. What's the highest modulation order? 64 QAM. It gives you Y in 64 QAM. Each symbol log to 64. So each symbol here carries how many bits? 6 equals 6. 6 bits per symbol, which gives you the highest data rate basically. Per each hertz, per each symbol, you are sending 6 bits. But for the case of PPSK, you are sending only 1 bit per symbol. QPSK, 2 bits per symbol. 16 QAM, 4 bits per symbol. But this is giving you 6 bits per symbol. Imagine you have 1,000 symbol multiplied by 6 is not going to be the same as 1,000 multiplied by 4. So this provides the highest data. So, next question. This is among the easy questions, I believe. Suppose you want to serve a user device with very high reliability. Now we talk about reliability. What's reliability? Reliability means that the bit error rate is extremely low. The number of errors you have in your packet is very low. So reliability is the opposite of data rate. So when I want reliability, I don't want to send too many bits per symbol. it's exactly the opposite. So in this case, which modulation scheme do I use? The one that PBSK basically, because it just requires 1 bit per second, per symbol. But the other ones, they are also in the bit error rate diagram. You can also notice that PBSK bit error rate is like this, but QAM is like this, and then the higher the modulation order, the more the errors in the modulation. Okay? The higher the bit error rate is going to be. So question 4, suppose you have a user using 2 different applications, video and messaging. Then what modulation schemes would you use for these applications to better serve the user? So you have serve the applications that the user. We have 2 users, one user, like let's together imagine the situation. We have one user, suppose this user, anybody, and this user is using his mobile phone or mobile laptop, whatever, and he's using WhatsApp. And what else? He's using also Twitch, okay, video, Twitch. 2 applications, Twitch and WhatsApp. Twitch we know is video service or YouTube. WhatsApp is a messaging service or call, depending, but if you are using it for message, it's going to be pure message. So for message, you don't care too much about data rate, you care about reliability. I want to make sure my message goes through correctly without any problem. I can tolerate delay, I can tolerate data rate, I can tolerate internet speed. Do you care if I send you an email and the email arrives after 1 minute? You don't care, at the end of the day it's going to arrive. But the most critical thing is to get it complete, to get it clear. I cannot tolerate an email that's written half and the other half is not appearing, yes? But for video, no, video is delay tolerant, video is speed tolerant. If the video is just hanging around and not playing, it's a problem. So for message, I need reliability, low bit error rate. And for video, I have high internet speed, which means high data rate. So which 2 modulations can give me this? So it's D, obviously, BPSK for messaging, this is the optimal, and 64 QAM for video, or Twitch. I can replace these with Twitch, or Discord application, or WhatsApp, or Signal application. You might, if you don't know these applications, you can ask about them. But like, I can replace them, I can extrapolate based on this question and say whatever I want. Suppose you have a user, and then question 5, suppose you have 2 users using the same application. Now this scenario is different. We have here, we have base station, and we have 2 users using the same application. Let's say they are using Zoom. But one of them is near to the base station. This is near to the base station, and the other is far. Then what modulation schemes would you use for these users to better serve them? This is near, this is far. What thing you should learn when someone is closer to the base station and the other is farther? The one that's farther from the base station, it means he experienced more path loss, more degradation in the signal. More degradation, it means he's in more need for reliable communication. He's in more need to have low bit error rate. So obviously I need to use lower order modulation here. And here, because here the signal to noise ratio is very low. And here I need to use maybe higher order modulation because the signal to noise ratio here is high. Because he's closer to the base station, there is no path loss too much, and therefore, if I show you the options here, you should be able to figure out which answer is the most correct. BBSK for far user and 16 QAM for near user. It's D. BBSK for far user. We don't have anything lower than BBSK, so we want high reliability for this guy. And we can tolerate, because here it's close, high STNR, it's not in a bad condition, I can speed the internet for this guy who's near the base station. So it's obviously D. So, moving on to MIMO. The capacity of fading MIMO system is always optimal. True, false, depends. I think it depends, but if you say false, because it says always, you are correct as well. So the capacity of fading MIMO system depends on what you use at the transmitter, how you optimally allocate the power, and what type of channel you have, what you do basically at the transmitter so that you get the optimal capacity. Here, the second question, beamforming transforms MIMO system into a SISO system with transmit and receive diversity. This question I need to modify it a little bit and be more specific by saying singular value decomposition beamforming. I cannot make it generic like this. It has to be singular value, because in this case, when we have MIMO system, you have multiple antennas here, okay, and you have multiple antennas at the receiver, and you have channel H here, okay? And here H, I can apply singular value decomposition so that it becomes U sigma V, okay? V Hermitian, or V sigma U Hermitian. And this basically, when you use it at the transmitter and you use this at the receiver, it becomes like, it acts like a beamforming, waveforming. Beamforming and waveforming, they are interrelated to each other. But this, what it does, it divides the channel into sub-channels. And these sub-channels are not interfering with each other. So instead of having one wide channel like this, you just divide it into smaller channels within this file. And this becomes like SISO, and this whole MIMO system is broken down to multiple SISO systems using singular value decomposition. And it's really, the correct answer is true. Beamforming transforms SVD beamforming, because this is different from the classical beamforming, where you really use multiple antennas to transmit the same signal, and you adjust, align their phases so that you decrease the beam width and you increase the range, and you basically concentrate the signal at the user side and increase the signal to noise ratio. But this is kind of different beamforming. We call it SVD beamforming. So question 3, the optimal use case of antennas in MIMO system is always multiplexing, not diversity. Of course, this is false. Like, it depends on the scenario. Basically, it depends. Depends is more correct than false. Because as I said, if the user needs reliability, you need to use space-time encoding. If the user needs data rate, you need to use maybe spatial multiplexing. If the user requires security, you need to use a technique that provides security. And question 4, MIMO receiver design usually trades complexity for performance. That's right. MIMO receiver design. The more complex the receiver structure, the better the performance will be. And the less complex, the less. Example, zero forcing is simple, but the bit error rate is not very good. But maximum ratio, maximum likelihood is very complex, but the bit error rate is very good. And question 5, the most complex MIMO receiver design is it maximum likelihood or linear predictor or sphere decoder? I think the most complex design is the maximum likelihood. So these are the questions. Thank you.